Hello again. This is Math 2233 coming to you from the College DuPage, and the title of this lecture is The Continuation of Kepler's Laws and Such. And as always, please be an active learner as you watch this video. So last time we proved Kepler's second law, that the position vector from the sun to a planet sweeps out area at a constant rate. This time we're going to address Kepler's first law, asserting that a planet moves in a plane. We've already done that, but now we're going to assert that it is moving along an elliptical orbit with the sun at one focus. Our first step is to discuss a thing called Hamilton's theorem. So in this section, we're going to show that the velocity vector v moves on a circle. Now we're going to let r, and this is a non-bold r, equal the magnitude of the vector r. And so what we knew from before is v dot, the vector derivative of v with respect to t, is always equal to the acceleration. And we also knew that the acceleration is equal to r double dot, but it was equal to minus gm over r cubed, and this is r. Now, if we wanted to change this from a vector r to a unit vector r, we would take r divided by the magnitude of r. So this would be vector r divided by the non-bold r, and so that's where the other r went. So we would have this, and we also know that the unit vector here is cosine theta I plus sine theta j. So that we've established this equation. Now what we're going to do is we're going to substitute for r squared. And we're going to use this equation that we have from before, where h, the scalar magnitude in the k direction, is equal to r squared theta dot. So if we solve for r squared in this, we would have h over theta dot. And so we substitute that into this equation. So that was r squared was equal to h over theta dot. So we substitute that in, and we get this expression. Now, v dot, by the chain rule, is the derivative of vector v with respect to theta times theta, the derivative of theta with respect to t, theta dot. So what we're going to do is we can substitute this on this side, and we'll see that the theta dots cancel. And so what we have is left that the derivative with respect to v of theta, derivative of v with respect to theta, is this expression. So this is the equation we had on the bottom of the previous chart. So we're going to integrate this with respect to theta, and we get this. Now this is the constant of integration, which is the v0 vector, and that's a constant vector, v0. So you see we have v is equal to this, so if we were to subtract v0 from both sides, the magnitude of v minus v0 is equal to a constant, because this is a unit vector. That means that v moves on the circle centered at v0 with radius gm over h. Now looking ahead, I'm going to ask you to try to remember that this is front and center in the Feynman lecture that I point you to later, and so just hold that in mind. Okay, so we've proven that, and that will be referred to later. But now let's go back to Kepler's first law. Okay, so now we know there is a v0, and we know what it is, and we can orient the coordinate system so that j is in the direction of v0. And that means that v0 is equal to the magnitude of v0 times j in that direction. So that means our equation for the velocity, this equation becomes this. Now notice that v0 is v0j, so what I can do is I'm really adding just a vector in the j direction, so I'm adding something for the j, and I'm going to call that e. I'm adding that in the j direction, and so that means I have to say, well, what was E when I add it there? And I want it just to be times J. And notice that I am multiplying this whole business by this on the outside, so I have to do a correction factor for what that is, and it's just an algebra equation, and you should verify this. But if I take E to be this, it works. So now we're going back to some of our basic principles. Recall that H was equal to R cross V, and that was H times K, where H was bigger than 0. And so I'm recreating part of that. But then you want to recall that R, this R, was R cosine theta I plus R sine theta J. And this V was this. Now there's a calculation. You have to take the cross product of those. I encourage you to test and make sure you do this calculation. But when you do that calculation, you get this, and this is in the K direction. And so noting that the sine squared of theta plus the cosine squared of theta, I can use the associative property, and I can call that 1. And so I had this is HK is equal to GMR over H, 1 plus E cosine theta times K. And now I'm going to solve this for R. Now notice that both sides are just vectors K, so I'm going to have that H is equal to this coefficient, and I'm solving for R. So solving for R, I get R is equal to this. And if I call this constant K, I have K over 1 plus E cosine theta. Now, at this moment, you might be saying, where is this going? Well, we're almost through, because I'm now going to assert that if E is between 0 and less than 1, that this is the only way this is going to be finite. And if something is in orbit, the radius is going to be finite. It can be a big number, but it is going to be finite. Now let's explore that. So in order for R in that equation to be finite for all theta, we must have 0 less than or equal to E less than 1. Now that actually would be an involved proof for me to put down here. You could do it, and maybe you should try to do it, but I'm just going to show you some examples. If I pick E to be 2, I get these red curves, which means you're going off to infinity. R is going off to infinity. If I pick E to be 1, I get the green curve. And again, R goes out to infinity. Not as fast, but it goes out to infinity. If I pick R to be 0.9, I get the blue curve, and it fits in there. So you see, that ends up being, we've sort of concluded that this is true. For R to be finite, for all theta, we must have 0 less than or equal to E less than 1. And that completes the proof of Kepler's first law. I remember when I saw this in my astrophysics course, I said, what? Why are we finished? I'm going to tell you in a moment. But first, before I leave this, notice that the velocity of a heavenly body determines its fate when it comes close to the sun. If it's going too fast, it will end up being hyperbolic, the red. If it's going too slow, it will crash into the planet. If it's going a little slower, it will exit in a parabolic arc, never to return. But if it is just right, between 0 and 1, it will be an elliptical orbit. But now we said, well, we're finished with the proof. Why is that? Well, I ask you to recall from your Calculus 2 at the College of DuPage that a polar equation of the form R is equal to ED over 1 plus or minus E cosine theta. It could be cosine or sine. We had cosines, I think. But this represents a conic section with eccentricity E. And this is an ellipse if E is less than 1. And E is always a positive number. And so that means that this is an ellipse from our derivation. And now we have proven Kepler's first law. A planet moves in a plane. We've already established that early. But then it goes along an elliptic orbit with the sun at one focus. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.